All right. Okay. Good morning. So it's so bad, and I don't know what our student looks like. So if someday you pump into me in the campus and let me know, hey, hi, Professor Wu, I'm your student in this class. All right. Okay. The first, let's discuss a very general theory, and the theory describe the energy relation, power and the power and the energy relation. If you can imagine, we have a system. Okay, this system could be a very small region, or it could be a very large region. Let's say, if you like to define in tens of kilometers, or if you can define in few millimeter size. Okay, it depends on what you are interested in. Okay, so in this system, you have, let's say you have a generator. Okay, then you have a lot of inductor. Okay, a lot of inductors and the capacitors, right? You have a capacitors, and also you have resistance, right? Okay, then besides, okay, you still also have energy going out. Okay, so let me put, this is in the form of electromagnetic waves. All right, okay. Then you can collect all the energy going out of this surface. Okay, going out of this surface. Then the question is, what is the relation between electromagnetic field? Okay, let's say if this is the voltage, right? We have a different voltage source. We have J. J is our very common source form, right? So I better use this notation. So the current source, okay, so J. This J is, we call impressed. Source. Okay, impressed source. That means that is the energy supplied by you. You see, for example, I take a very simple antenna, a dipole antenna. Okay, so I have a feeding line. Then this feeding line, I have a current. Okay, then this is a very simple antenna. Then we have this current. This current is formed along the dipole. Okay, so there's oscillating back and forth, and then radiating. Radiating electromagnetic field, right? So we will have more derivations of this particular solutions, okay, by yourself, right? So we are going to have them. So, right. So for such case, we have a current J, right? Then if we like to include this to see how much energy transmitted. Okay, so this is a very specific problem, right? Okay, now let's find the relation between how much energy transmitted how much energy stored. Stored energy. Okay, what components that can store is inductance and capacity. All right. Okay, let's say what is a general relation of this problem. This is what we are going to discuss today first. Okay. So we use a vector, we call vector identity. Okay, we call identity, that means no matter what is the physical quantity is, this equation is always true. So we don't prove it. So this is a very common and vector identity. So this vector identity tells us if A and B are arbitrary vector variable because we are taking differentiations, right? We still remember what delta means, right? The delta is a differentiator, vector differential operator. Okay, so this is just the operator. Okay, differential operator. Then if you have two vectors cross multiply, okay, then take divergence. Okay, then what's that equal to? Equal to all right. So we use this vector identity like A we take is our electrical field intensity, right? And the B is magnetic field intensity. Okay, then we substitute them into this. Okay, then we have this general expression. This is always true because mathematically it is true, right? Then from here we don't know what the E and H is so far. It's just a symbol, right? We have to give life to them. So what the life is, okay, then we know the curl of electrical field related to magnetic field B through what law is this? Faraday's law, okay? Through this Faraday's law, okay, we substitute this Faraday's law into the first term, and we also know the curl of magnetic field H that follow the Amps law. Amps law include impressed current, okay, the current. And also the second term is also a current. This current is called displacement current. Okay, the second term is displacement current. The displacement current. So once we substitute these two into this general vector identity, then we give variable E and H life because that has a specific physical meaning which is a Maxwell equation. Then we know E and H is electromagnetic field. Okay, before we inserting these two equations, E and H is just a symbol, right? You can call anything, you can call A and B. Right? Okay, then what we have, we substitute the curl E and the curl H, then we come to this equation. Okay, this equation, let's copy it. Okay, let's copy it. Then let's study one by one. Okay, term by term. The first term is this. Okay, first term, because we know the B is mu times H. We are going to discuss this we call constitutive relation. Okay, constitutive relation. So we are going to discuss this in the next hour. Okay. The B we call magnetic flux density, and the H is magnetic field intensity. Let's consider in free space. Okay, in free space, B and H is related to the permittivity, the permeability in free space. Okay, which is a physical constant, right? So we replace B by this, and because the derivative with time, the derivative with time is just okay. I can consider this term as okay. If we have say f square partial x, how we do is we take derivative with respect to this. So this is 2 times f, right? Then df dx. Okay, we use this relation to here, right? We use this relation to here. So let me say this term we can consider is a multiplication. Right now I use dot product or scalar vector product because here is a scalar vector product. Okay. Then scalar, a vector, dot vector itself, we know this is the magnitude of this vector square. Okay. Or simply we write like this, right? So this is the first term we have. So this becomes scalar. And the second term related to electrical field, we also know the constitution relation. Okay, we also know this relation by using the same rule. Okay, we have another power relation. Okay, so let's leave this to this equation 1, 2, 3. Let's look at the third term. The third term. The third term, actually, from time to time, we also use this is because we use another constitution relation. Okay. We use another constitution relation. Let's copy this. We use the 3 constitution relation. We replace this, the J, by this is conductivity. The conductivity of medium. The conductivity for different medium, a different value, right? For conductor is a material is very, very high. Okay, as high as like for silver, right? So it's about 7 something, okay, and 10 power of plus 7, okay. Okay, then if for the dielectric, it's very, very small. Okay, it's as small as 0, right? Okay. Then this relation, also a scalar relation. Now equation 1 become this, okay, becomes this. The first two terms is related to the time directivity. The last term, which is copy here, right, which is copy here. Okay, so this is a very important relation of electromagnetic wave at any point, okay? So in this case, the current J is no longer impressed current, okay? The current J can be formed because of electrical field, okay, because of electrical field, and then driving by the conductivity in the medium, okay, driving by the movable electrons, okay, the movable electrons around the molecular in the medium, the electromagnetic wave exists, okay. So this J is replaced by the electrical field. So as long as you have electrical field exist, you have a current, all right? So this relation is true at every point in the space, okay? If ask you to give me some description, what is electromagnetic field? Okay, think about this question. If I ask you, or somebody ask you, hey, you learn electromagnetic waves, right? Tell me what is electromagnetic field? All right, sure, you can have very academic answer is you write down the Maxwell equations, okay? You write down the Maxwell equations, okay? So by Faraday's law, right, and Ohm's law. So this is one way, okay? This is one way. You said you define two vectors, okay, and the two vector variables that change with location, right, and also change with time. That satisfies this relation. Okay, so that is Maxwell equation. Or you said, okay, we have two field quantity, E and H, and at any point in space, okay, as long as they satisfy this relation, these two variables, E and H, one is called electrical field, one is called magnetic field. All right, okay. So I emphasize this relation is true at every point around you. All right. All right, okay. Let's take a look of the integral form. Okay, let's take a look of the integral form. The integral form of equation. Integral form of equation 4. Okay. This is equation 4. So if we take a volume integration on both sides, volume, okay, we take volume integration on both sides, then using a divergence theorem, okay, this become surface integration. Okay, this become, right, if any variable, okay, if any variable satisfies this relation whose divergence is the curl of this volume integration, so this equal to this, right? We prove this. Okay, so this is a surface, this is volume. right? Okay, surface and volume. So that is a relation we already started. Okay, then the left-hand side become surface integration. Okay, sometimes I use this, sometimes I use this, but this is something. Okay, this is something. It's all indicate the surface integration over a closed surface, over a closed surface. Left-hand side is clear. Okay, what is clear? When we mention what does this mean? This means a collection of all flux over S, right? Because that means for any vector A, if this is vector A, I take a normal component. Okay, this is normal component. I call this called flux, because the normal component, that means the field line go out of surface. Okay, then I collect a very small differential surface and multiply this normal component every point over surface and add them up. That is this surface integration. That means a flux. So in this case, what is A? A is a very special variable. I call vector P. This P has a very specific name. Okay, this name after a scientist appointee. So we call a pointing vector. Pointing vector. So pointing vector tells us, okay, let me explain the right-hand side first. Okay. So this term called the pointing vector. Okay. Now let's take a look at the right-hand side. Right-hand side, we do the volume integration. Okay, volume integration. So the first term is nothing but the stored electrical energy. Okay. I'm talking about whatever inside of the integral. Okay. Inside the integral, the first term is stored electrical field energy, because this stands for energy. Okay, and also related to electric field E. Okay. The second term related to stored magnetic energy. Okay. Then we collect, because volume integration, we collect all the energy, okay, contained in the volume, and then to say how it changes with time. How it changes with time. If it doesn't change with time, then the directivity equal to 0. Okay, there's no contribution to the left-hand side. What is this case? This is DC case, right? This is a DC case. That means if this is a direct current, okay, if the DC case, then equal to 0, right? Okay, that equal to 0. Otherwise, it contributes to P, right? To the pointing vector. Okay. The third term is clear. Third term is just power dissipated on the resistance. Okay, dissipate on the resistance. Because conductivity, so 1 over conductivity is resistivity. Right, this is the resistivity. So the third term is consumed, the energy consumed. Okay. Now, what that says is pointing vector. Let's go back to this picture. Okay, we going out, we have a pointing vector is always E cross H. Okay, E cross H. That is energy. That energy is, this could be complex number. Okay, then if you take a real part of it, that means a real energy. If this surface is very, very large compared to your antenna size, so that means this energy is related. How much energy related? And then if the surface is large enough, you only have energy related. Okay, then that is become a real number. And how the energy is created by the stored energy, electric field and magnetic field change with time. Okay, so it's change with time, this is oscillating. Okay, if you change with time, so that create energy going out. Okay, of course, the energy that created, by this, okay, even though the minus sign, that means the create energy. Okay, minus sign means create energy, right? So you see why minus sign is create energy. Of course, if we study the Ohm's law, what we define, if the Ohm's law, this is voltage R, current in, right? Okay, so what your consumed energy, the consumed energy is RV square, right? RV square. Then you see, because this is I equal to this is I equal to V, right? So I equal to V. So I is, oh, right. So this is the energy consumed is positive, right? So if this is a battery, the current will be going out, then this energy we call minus. So that means when we put a minus sign, so that means deliver energy, okay? Deliver energy minus consumed energy, okay, by resistance. This is consumed energy. That equal to the total energy going out of the surface. This is basically, you can call energy conservation law for electromagnetic field. So let's recall the example, the electromagnetic field example we discussed when we talk about the wave equation. What we assume is, if this is X, we have electrical field, we have a magnetic field, right? Then this is the wave propagation direction, right? Then we said, when the wave propagates in positive z direction, we have a solution. That means E cross H. E cross H, using right hand, the thumb point to the direction of wave propagation. This is inconsistent with pointing vector. Okay, P, the direction of P stands for power flow, energy flow. Okay, the direction. Do you remember we also say this is if I put a plus sign, that means the wave propagate in positive that direction. Okay. E cross H, right? this is in P direction, in positive Z. Okay. We also, do you remember, you see, for the reflected wave, or not reflect, for the wave propagated in minus Z direction, magnetic field has a minus sign. So in the other case, we have the electrical field in minus Z, propagating in minus Z direction, cross minus H. So in this case, minus H refer to propagating in minus Z direction. Okay, so this is the P vector, which is a vector. Okay, for the wave propagate, this is a P direction. Okay, for the other case, so this is a magnetic field. Okay, for propagating toward minus that direction, this is Z, right? Because X, Y, Z is always held by right-hand rule. Okay, so in this case, E cross H, but if H is polarized in minus Y direction with respect to E field, so this, the P is in minus Z direction, this is in plus Z direction. Okay, so that is the answer. You see why, you see we have a minus sign in front of magnetic field. Okay, one, the wave propagated in opposite direction. Okay. Okay, let's take a few examples. Okay. Then if we like to, we have a plane wave. If assume we have a plane wave. So this plane wave, we assume propagating in positive Z direction, and the electrical field polarized in X direction, and the magnetic field polarized in Y direction. Let's recall we said for plane wave, we always have a relation is the magnitude of E over H equal to a constant in free space. So-called in free space is infinitely large and is very ideal, like a vacuum. Okay, vacuum. So in that case, the wave intrinsic wave impedance is a constant. Okay, we said this is so easy to remember, 120 pi. Okay, but in lossy media, okay, in lossy media, this Ex over Hy still a constant, but not that lucky is because we have a loss. So this wave impedance is constant, but it's not a real number. That become complex number. Okay, in complex number, then I write in this way is okay, I write in magnitude and phase. Okay, we are going to discuss how to find it. Okay, how to find this complex wave impedance later on. Okay, now in this case we use this relation. Okay, now we use this relation and in this, the magnetic field become E field divided by the magnitude. So where is the phase term? Phase term come here. Okay, phase term come here. And this operation require a knowledge we call phasor. The concept of phasor is very important. I don't know how to emphasize it. And suppose we should learn it very well in circuit theory. Okay, in circuit theory. That is particular for electrical engineering. Okay, we use phasor all the time because phasor is make our manipulation derivation very simple. And how to answer this question is this constant term, okay, come to the cosine, the phase term, and it's very easy to explain using phasor concept. We will find time to further review the concept of phasor, because in EM wave analysis we also use phasor all the time. Okay, if you don't have deep impression on the concept of phasor, go back to review your textbook on circuit theory. Okay, now we have E, we have H. Now we can calculate the Poynting vector. Okay, E cross H, because one is in X, one is in Y component, so that's easy, right? So E cross H is the result in a vector in that direction. Okay, in that direction. Then the result first is a function of location, which is Z, and also a function of time. Also a function of time, right? So, but that means the function of time, if this signal, we can say how fast, how this signal change with time is sinusoidal, right? Because we use the cosine function. So this is sinusoidal waves. So the time variation is very simple, follow a sine cosine function. And what is the frequency change? Frequency system, right? Because omega t, omega is a frequency, right? So the omega equal to 2 times frequency. Okay, that means this signal change with time very, very fast. So that means we are not interested in the instant Poynting vector change with time. Okay, and what we are most interested in is the average. Okay, average over one period. Okay, average over one period. We take average. So we use this concept, average, all the time. Say, so after final exam, and then the teacher need to take average of the score of the whole class, right? To say if this is in the medium level, right? Okay, so that is average. So we have a lot of applications using average, right? And because we are not interested in a particular things. Let's say what is the average price for the groceries, right? And then if this has been increased compared to the last month, so that is average. Right? So we take average. That means we take integration over time for one period. T is a period. Period of what? We say if this is time, this is a signal, because sinusoidal signal, right? So from this point to this point, This is a period. Or to any waveform, to any point, this is also a period, right? This is also a period. So we take integration over one period. Okay, so the period is 1 over frequency, right? Then we divide, so take average, right? Then normalize to the period, right? And that makes sense if your t is very small, okay? Then your integration, no matter what, will be very small, right? Then I divide the period very small number, so this ratio is not very small, right? And then after you take a derivative, integration, take average, then you get constant value. Then you say this value depend on the phase, depend on this phase, depend on this phase. If this phase, you can say, if this phase happen to be 90 degree, if this phase has to be 90 degree, that means electrical field and the magnetic field is out of phase. It's not out of phase. It's 90 degrees phase difference. What is the result? What is the result? The power, average power, will be 0. Okay, so that means one electrical field and a magnetic field with 90 degree phase difference, you have no energy. You have no energy going out, or you can transfer, right? Because average is 0. Okay, average is 0. This is the one fact. The second fact, you say if this phase is very small value, okay, very small values, that means if you have electrical field, the magnetic field with a very, very little phase difference, okay, that means, okay, the most of energy still there, okay, still there, not, you didn't lose too much, okay. And also another thing is the alpha. I'd like to draw your attention on alpha. This alpha comes with the original field expression. You see, this alpha we call attenuation. Attenuation constant. That's also depend on the alpha is a function of conductivity. Okay, alpha is conductivity. So this wave impedance is also function of conductivity, and not only conductivity and also frequency, So if you have a loss, okay, so once the wave travel, once Z increase, this attenuation factor decrease exponentially, okay, exponentially. So eventually it will die off, right? Okay, so this is a example about the plane wave, okay. Let's take a look of another simple example quickly. Is we have a DC current, okay, direct current, that means DC current, okay. The DC current means that means the change with time is 0, okay. Change with time is 0. Okay, so what that means is we have a very long, straight conducting wire, okay, very long, okay, very long. Then we have a current, we have a total current I. So because this is a DC, the current is uniformly distributed, okay? Uniformly distributed across cross-section. Because the reason we like to have this is I can find the current density, okay, density function, which is uniform, right? So this is total area and then total current divided by total area of the cross-section, and the current is flowing in the z direction, is in the z direction, okay? Then from the current, because we have conductivity, okay, the current is driven by the electric field. In this case, the current is driven by electric field, right? Okay, then we can find the electric field, okay? We like to use this case to verify or to take a look in this DC case, what a story the Poynting theorem tells us. Okay, Poynting theorem tells us that we have electrical field. We can also find the magnetic field because we can use Am's law. We use Am's law, we can find the magnetic field, right? Because we define a contour C, and then the magnetic field, the contour C, they equal to total current. Okay, equal to total current. This is Am's law when the displacement current equal to 0, right? Then because H, we know using Poisson law, right? The H is in the direction of current cross the R, the current in that direction. This is R direction. Current Z cross R is in phi. In phi direction, okay, in phi direction. So, and also the magnetic field is uniform in any angle, right? So that is a constant, which is independent to the phi. But however, we collect the magnetic field over the outermost surface of the cylinder. So the distance R equal to B. Okay, this equal to B. So we find the magnetic field. We find the electrical field, we find the magnetic field. Now we can find the Poynting vector and the E cross H. Okay, and the E cross H. So now you see this Poynting vector result because this the phi direction, right? This is phi. So Z cross phi point to minus R direction, okay? Point to minus R direction, right? Because Z R phi, right? Okay, so we have a minus sign. That means the power is go into the conductor. Okay, when the current flowing in this way, in that direction, the power go into the conductor. Okay, because this is what this minus sign means. Okay, and the minus R direction means, right? Okay, this is a Poynting vector. Okay, Poynting vector is still the power density. Power density is not the total power yet. Then let's calculate the total power. Okay, if the energy is go into it, right? Then I define my normal direction is go into it. The normal direction, the ds, which is differential area, okay, that equal to minus R direction ds. Okay, in this case, so why do the surface integration? Okay, and also you see because the P is only in R direction, there's no component in Z direction. So the surface integration over this two surfaces 0. I don't need to worry, right? So this closed surface, if I conduct the surface integration, I only need to conduct a side surface. Okay, the side surface that equal to 2 pi times b times b the radius, that means the total length of periphery, right? And then the L is the total length. L is the total length, total height of the cylinder. So this is the total. That means this is total surface multiplied by this power density. Okay, and then this also very easily we can find what is this. This is just the resistance of this cylinder. Okay, this is the resistance of this cylinder. What resistance? The resistance is resistivity. That is 1/sigma, right? And the resistance is proportional to the length of the cylinder. Okay, and inversely proportional to the cross section. Okay, the cross section of this cylinder, what that is b squared pi, right? So b squared pi. So this is the total resistance. Then you see that equal to exactly what we expect. Okay, the energy, because it doesn't change with time. Okay, energy couldn't, no energy go out of the surface, and all consumed by what? By the third term of Poynting theory, that is consumed over resistance loss. Okay, so that energy is balanced. All right, and the Poynting theorem, we have a form, the circuit form, okay, or circuit representation. If we have RLC, okay, as a circuit, then if we look at the total power delivered at these two terminals, okay, then that is V times I, voltage times current. Then we can see V times current is the total power that equal to stored energy. Okay, that's stored energy. You see, because this stored energy, right? Okay, the stored energy change with time plus consumed energy. Okay, plus consumed energy. So that is a circuit theory. That is a special case of a Poynting theory. Okay. So I take too long for these materials because it's very, very important. I try to explain it as much as I can in this limited time. And let's take a break for 5 minutes. We resume our class exactly at 10:30. Right. Okay, so let's come to chapter 5. Okay, chapter 5 we are talking about fields and waves in material media. So that means how to describe the interaction of electromagnetic field with different media. Before what we learned is Maxwell equations in free space. The free space means ideal vacuum, right? And then we didn't consider the interaction of the field with material. Okay, then in general we categorize the material into 3 types. Okay, so depending on how what the interactions is, right, and also the basic property of the material. So the first kind we call conductor. Second kind we call dielectric. And third kind we call magnetic type of material. Okay, so that you see that respectively related to you see the conduction. Okay, the conduction of electronics. Okay, we call conduction phenomena, and also the second is related to the polarization phenomenon. Okay, and the third one is the magnetization phenomenon. Okay, so from study of these three phenomena, then we are going to build up we call a constitutive relation. The constitutive relations. Actually, we already used constitutive relation just now, right? And but we didn't go into the detail. So the constitutive relation, we said one is the current, right? And then we use this, right? And then we also use so that three constitutive relation we already used. And why we use these relations, then the interaction of the field with material, you can go as deep as the interaction with molecules of materials. Okay, you can deal with electrons, right? Okay, but that microscopic world is too small for us to model, okay, to understand. We cannot say, hey, why I want to study the field interaction with, let's say, with my body. I cannot study every molecular on the materials, all right? The interaction, that is a microscopic description, okay? And instead, we like to look at the field relation in the macroscopic. That means in a large scale behavior, what that is, okay? So this is, we can say, this relation is more or less the description in macroscopic world, okay? So that save us a lot of effort and time to look at the molecules, okay? But however, to understand those things, we still like to start from the very basic description from molecules, even from nucleus, electrons, okay? We know for materials, right, and then when we apply electrical field, and then there is interactions between molecules, the inside, and then the field, okay? Then we take a classical model of material. That means the molecular, we have atom. The atom contains, we have a tightly bound electrons, okay? Those electrons tightly bound to what? To the nucleus, okay? In the nucleus, we have protons, we have neutrons, okay? We have protons and the neutrons, and we have a positive, so that contains a positive charge of nucleus, okay? And surrounded by electrons. So surrounded by electrons, we have two types of electrons, right? And for some material, okay, more tightly bound, we call, okay, tightly bound electrons with the nucleus. Okay, and also for some material, we have a more free moving electrons. Okay, we call electrons cloud. That is a free moving. And then also there are some type of material, okay, and then not so easily bonded, and then easily be released from nucleus or by any thermal agitation, okay, or excitation, thermal excitation, say when the temperature goes high, right? So that will be released and will be recaptured by its own atom, okay? So because of those very basic, those differences in the very basic property of the electrons, okay, that we divide materials into semiconductor. Okay, let's talk about conductors first. Okay, so in this case, we have a lot of cloud of electrons. Okay, a lot more electrons freely moving. Okay, freely moving around the nucleus. But however, without external field, they just randomly moving, and then you don't see any clear current, okay, moving in one or other directions. Okay, so that direction is random, but however, they are ready to be driven, okay, to be driven by electrical field. So those we call a conductor type of materials. Okay. So that means for conductors, if we have electrical field, okay, then the field, okay, let's say if we have a battery, we have electrical field in this direction, then we know the positive charge will be appear, right? And then the negative charge will be attracted. Okay, so they are moving toward opposite direction, form a current. Okay, forming a current. Another material, okay, we call dielectric material. Okay, for those materials, the electrons is tightly bound to the nucleus, and the very few electrons you can be driven by electric field. Okay, so it's tightly bound to its own nucleus. Okay, so even though you apply electrical field, okay, you don't see the obvious current moving around. The third type we call semiconductor means we have two types of carriers. One is electrons, one is holes. Okay, then some we call the holes, also we call the vacancies. Okay, so under certain electrical field, so those holes can break the bond with the nucleus and then move to the other neighboring electrons, neighboring nucleus, or you see a moving more, right, distance. It depends on the electrical field. So it's people find a way to control the movement. That is why we have today's semiconductor device, right? We know how to control the voltage and how to control electrical field, and then to manipulate the distribution of electrons and holes. We can form PN junctions, okay, and then we can form channels, okay, between drain and source and drain, okay, controlled by the voltage from the gate, right? So that form transistors. For those type of material, we call semiconductors. But semiconductor is not a subject in this class, okay? But we just briefly mention this. All right, so so the simple and the relations. So the simple and the relation between electrons movement we describe by the conductivity. So this is movement of electrons. Okay, we use a parameter to describe it in a macroscopic domain. Okay, so we don't look at each individual molecular or use nucleus or electrons, right? That will be too much. That will be too much work. Even though today people really have some very intensive research to try to use a supercomputer to model all the details and then try to synthesize a high performance semiconductor by controlling electrons movement. And then a couple of years ago, I attended a seminar, physicists doing the simulation, how to design a PN junction, okay, by modeling that. Okay, that is out of our scope. Then this we call Ohm's law. Ohm's law in the any point, okay, in any point in space, okay, any point in space. In this case, with this constitutive relation between E and the current, then we can replace this current we call the conduction current, okay. So say mean the conduction current by this law, okay. Then I also list the conductivity, okay. The conductivity, just now I mentioned for the silver, the conductivity is about 6. Just now I mentioned it's about 7, right? It's not accurate. So it's about 6 power 10 power of 7. Okay, that is almost the highest conductivity people can use. The silver with the highest conductivity, that is true. Okay, and but also is the problem for silver is very easy to be oxidized, okay, when you expose in air. So what is the most stable metal, okay, that subject to the oxidation is gold, okay. So you see, it's almost, you see all the ICs. So it's the end, you have to play a layer of gold to maintain the reliability of the metal. So you heard, you say, in suppose this year we have an Olympic game in Tokyo, right? So the Tokyo all Olympics, they propel the gold medal. The gold medal is recycled gold from all the old phones, okay, mobile phones, to recycle the gold from old phones. Okay, so that is the conductivity. Now let's look at dielectric. Okay, if I put a dielectric, we said we have a nuclear, we have electrons, but bonded, all right, bonded to the nucleus, those electrons not moving away, okay, not moving away. But however, you see, when we apply electrical field, okay, one nuclear, we have electrons. When we have nuclear is a positive charge, electrons is negative charge. So when we apply electrical field, then they move slightly, okay, they move slightly. So the nuclear, so if the electrical field in this direction, the electrons be attracted upward, move a little bit, and the positive charge nuclear move slightly. okay, downward, but they still bonded together. I'm talking about one nucleus, okay, and we have, I don't know how many, okay, then all moving in the same fashion. So this positive and negative charge slightly move away a little bit, form we call dipole. Okay, di means two, right? Di means two, okay. So we polarize into two, like this is dipole, okay? We have a very small distance, very, very small, okay? Then once the electrical field reduced, strength reduced, but the direction not reduced. So the dipole, the distance become closer, and then if once, because the field change with time, right? With time. So after omega t equal to pi over 2, so direction change. So polarization also change, right? Polarization also change. So those pictures describe when the electrical field is highest, lower, okay, becomes 0. So there's no dipole, okay, and the change in direction. So the dipole change the direction, okay. Again, repeat and oscillating and oscillating. So this is what happened within the dielectric, okay. What happened within the dielectric when I apply electrical field. Okay, so those form dipole, okay. I collect all these together. I collect them all these together. This like, you see, because I have so many of them, right? So I collect them in a certain volume, even though you see I have minus, minus, minus. If I look at a certain volume, you always have a net charge. This net charge is a positive or negative, okay? Because you have a dipole, you have a certain distance. So all this collected dipole, okay, I call polarization density, okay. I call polarization dipole moment per volume, okay, P. This dimension basically like a charge, okay, like a total charge. So we know the current continuity relation, right? So once the total charge with time, that form current. So therefore, we need slightly modify our Am's law. This is original current in free space, okay? Original current in free space. So this is a newly introduced current. That is current formed by the polarization, okay? Then this is original displacement current, right? So this is replaced by this relation and so on. So we can rewrite it, still rewrite Am's law in the same form as in free space, right? Because right now in free space, we are in this form, but however, in this case, instead of, okay, the originally we call D, right? But now it looks, we have a new member in the family, which is P, right? Also, by doing experiment, people say, hey, this P is related with electrical field. In isotropic, what does isotropic mean? Isotropic means that the property in all the direction is the same. Let's say if I gave you a material, I give you a material, so don't look at it as a mouse. It look like a piece of dielectric. So if I apply electrical field in this direction, or this direction, this property is the same. Okay, this we call isotropic. And then the opposite of isotropic we call anisotropic. For example, some material, strictly speaking, is anisotropic, the property. For example, the FR4 PCB board, circuit board, because it's made by layers of fiber optics. So it's a layered problem. So the field in this direction or that direction, strictly speaking, not equal. Okay, but because difference is not very high, not very large, so we still treat it as isotropic. Okay, once this is isotropic, okay, we replace the P, right? We replace this P. This we still define as D, okay? D is electric field flux density, right? Then this P come into this, then the D we can write in the form like this. Then epsilon 0 is clear, right? We already I gave the material. We know how to determine it in free space, which is constant. Okay, that is free space. Then after we found this relation, then we found we need to, for given material, we need to introduce another parameter we call relative permittivity. Okay, this is a free space permittivity. This is a relative permittivity. That means relative to the free space. Right. Then when we multiply together, I call absolute permittivity. Okay, this is again, this is a description in macroscopic view. Right. Then that describes the relationship or the interaction between electric field and the material. For different material, we have a different relative permittivity, right? This relative permittivity can be measured. Okay, can be measured. Okay, I keep saying, you see, for, we call FR4, you know FR4? FR4 is a material, is for PCB board, printed circuit board. Okay, that is material we have to deal with, right, as electronic engineering student, right? So for FR4 PCB board, the epsilon R is in the range. Okay, in this range, it depends on the manufacturing and also depends on the frequency range you are working, right? So we need to remember this. Okay, we need to know this, at least after you're taking this class, right? Okay, so this is the interaction between electrical field and the dielectric material. Even though you see, we said we talk about electromagnetic field, these two always go together, right? But we still treat the electrical material and the magnetic field material separately. And then that's true for most of the material, that the magnetization property is almost zero. Okay, we only need to care about electric property. And for some special material, which we call magnetic material, okay, this is a special type of material. For those special type of material, we have a lot of special applications. Okay, we have special application, but in most of the time, the electromagnetic problem, and that is a very special area, because not only the application is not as many as electric materials, but also the mathematical description is more complex than helical field material problems. Then also again, you say we can find kind of we call magnetization vector. Okay, we call magnetization vector M. What is M is formed? What M is formed? We said for certain material which is not a conductor, and then not ordinary dielectric, the electrons is the electrons moving around. Okay, when you have magnetic field applied, when you have original magnetic field applied to these materials, the electrons not only its self-spin, okay, not only self-spin, but also they rotate along a certain axis, moving certain axis. So when electrons moving along a certain axis, clockwise or counterclockwise, okay? So that form a current, okay? I just like you to draw attention to this. So that movement for a current, okay? This current generate actual magnetic moment. You see, if current moving in this direction, we have magnetic field in this direction. So I collect all this extra magnetic field. I form another moment. Okay, I collect every electron, the movement. Okay, then I have a net magnetic field. Okay, same as we have a net electric charge because of the dipole. Okay, dipole moment of positive and negative charge, and then we have M, that is actual magnetic field. So the next actual magnetic field that proportional to the original B. This is proportional to the original B in this form, okay, and also because this M is in the same quantity as H, okay, as same quantity as H. So the curl of this proportional to the current density, okay, then we modify the free space, epsilon by adding extra term, the current, which is formed by the spin of the electrons along a certain axis, okay, the orbit, moving over the orbit along a certain axis. All right. So basically it's a collection of all this, okay. So the net, so when I have this current, I have a magnetic field moving, pointing into the paper, okay, into a screen. So this current is formed by the curl of the total magnetic moment, and then I move this term, and I move this term toward left, which results in this. The reason I move toward left is then I can define this as a new edge, okay, as a new edge. This is a new edge, okay. This edge is a total edge, not, and then the original B is the B in free space, but this edge is not in free space. This edge is inside the material, okay. So inside the material, Having understood this, we can modify the original Ampere's law in free space by modifying this is original H equals 0 in free space. And then this term this is original H without the material. Okay, then this term is my new H inside the material. Okay, inside material, right? So after having this, then my new Ampere's law is clear, right? So that's still in the same form as the original equation, but now I have to state that the H must follow the constitutive relation with B. Okay, we know what B is, right? So B is original one without this material, right? Okay, so now we put this relation. Now we can use the same original Ampere's law integral form. Okay, so far we introduced the three constitutive relations, right? Right. We have three constitutive relations. Now we have H. Both this relative permittivity, you see, because mu. So the mu is free space permeability times relative permeability, and then the absolute permittivity equal to free space permittivity times relative permittivity. Okay. Okay. Then we can see for most of materials, the permittivity, for most of the material, the permittivity, even the metal, okay, for most of for dielectric permittivity, permeability, definitely you don't need to worry, that equal to 1, okay. But for metal, but not all the metal is magnetic type of material. For silver, for copper, for gold, aluminum, brass, right, bronze, tin, lead, nickel, all those, you see, that mu equal to 1. That means the permeability is the same as free space. Only for those very special material, but like stainless material, you're pretty high. That mu is pretty high, right? But for some material, you have very, very high value, okay? And the people can make use of it, okay? And also sometimes we use called ferrite material, and that is a highly anisotropic material. So for different directions, the permeability is different, okay? And the people make use of those properties to make many very unique devices. And I don't know, in your generation, have you ever seen any floppy disk? For floppy disk, before we have a solid state memory state, people use floppy disk, right? Floppy disk, we insert, I don't know how about CD. Yeah, CD is also, CD is not floppy disk, okay? So floppy disk is, you can easily rewrite, right? So for floppy disk, that is a material, a magnetic type of material, okay? Magnetic type of material. And then we use that to save data. Okay, save data. And why was a graduate student, we use floppy disk with that large size? Okay, that means because the density is poor, we have to use a large area to store very limited data. But at that time, in 1985, when I started, 86, when I started study my PhD study, I always use very large floppy disk. Using floppy disk, people use a very important property. What that property is, we call hysteresis. Hysteresis. What is hysteresis means? Okay, let's look at this curve. Okay, that is a hysteresis curve for ferromagnetic material. Ferromagnetic material. What that means is, okay, suppose in the initial state of this material, okay, then before you apply any external B, okay, where H is 0, B is 0, okay, H is 0, B is 0. So when you apply B, you increase B, you increase H. You increase B, you increase H, right? You say you have another B, you have another H, right? So you increase B again, so you increase H. And then you also will come to the point B, all right? Point is too high. Okay, you come to the point B. Then, okay, then you reduce B. When you reduce B, okay, H is also reduced, but not in the same amount as the way, if I call this is two ways, okay? So this is one way, okay? You go from Hong Kong to New York. When you come back, okay, you don't take the same route. When you reduce B, it comes to this way, and you reduce B, okay. When you reduce B to this level, to a certain level, H is 0. Okay, and then you further reduce B to 0. H is opposite direction. So that create one bit of signal. Okay, so your magnetic field stopped. Then H still remain. Okay, so you remember, say 0, okay, for binary code, right? For binary information. Then if you apply offset B to this level, okay, and then you increase again, the B stop, you come to another H, okay, then you increase B again, so they come to this point. So this curve we call hysteresis curve, okay. So that material tends to be, you have such unique properties, okay. So people use this for memory, but sure, today people don't use such technology, right? But this technology, I think, still being used somewhere, okay, if the density is not very critical. Okay, in summary, we have Maxwell equations. We have a Maxwell equations in different medium. Okay, Maxwell equation, we have Faraday's law, but now B and H is related to by this. Okay, we have Am's law, same form as free space, but however, the D and the current J, right? So current J is related by this relation, and between D and E is related by this relation. All right, so this is a more general description of maxwell equation inside the material. And if you are curious, you may ask, what is the relation? What is the relation between, if I have two different materials, okay, say air and the material, what is the property of electromagnetic field between? That is called the boundary condition. We are going to discuss next week. Okay, that is the boundary condition. All right, so we have critical timing. Okay. So, question. So I couldn't see your face because you don't like to show your face to me, or show your face. I couldn't see your facial expression. I don't know how much you understand from your facial expression. Can you show me what question you have? Or very well understand? Okay, so I stop here. So I will be in the room for a little while, and if you like to talk to me or you like to post question on chat, welcome. Okay, let's stop here today.